So this is hopefully quite a quick video on section 7.4 on solving trig equations. Now, if you're watching these videos as a playlist and working your way through them, what I said at the end of 7.3 is really what's going on here. Everything we already know, we can apply it. Now that we've got these double angle formulae and these angle addition formulae, we can apply those to solve the trig equations, but the technique for solving trig equations hasn't actually changed. So let me start with example 11 here. Cos of 2x minus cos of x plus 2. Well, what I need to do if I'm solving a trig equation is turn it into a formula that looks like cos x or sin x or tan x equals a constant. So down here, look, we've got to what we wanted. Okay, cos x equals minus a third or cos x equals a half. Those I can then draw the graphs and find the values and do all the rest of it, or use the cast diagrams if you like that method of finding whether the things are positive or negative. But from there, we can do this technique. So what do we do? Well, when we met with a trig equation where we don't have something that looks like this, we need to make it look like this. We need to simplify it until it does. And the way we do that is we use our identities, we use our algebra tricks, we use whatever sort of cunning we can come up with to reduce it to something of this form. Now in this case, I've got a cos 2x and I've got a cos x, and I need to realise that I can't combine those two together. That's not a good combination. So I need to write cos 2x rather, in terms of just coses and sines of 1x. Now in this case, I don't want to introduce a sine squared. I don't want to write this as cos squared minus sine squared, because then I've got cos x and sine x all in the same equation. So if I use the version of the identity that has cos squared in it, and I replace the cos 2x with 2 cos squared x minus 1, then from here we should be plain sailing, because this is an example that we've seen before. Now I say we should be plain sailing, doesn't necessarily mean we are, because this is quite a difficult kind of a question. So it's a really good example, this section, that you need to know everything that builds up to this. This is one of the harder chapters in the second year A-level course. You need to really know the techniques from the first year A-level course trig chapter, right? So the AS level course. So here, once you see this, you go, this is fine. I've only got cos x's, and this is a quadratic in cos x, so I'll factorise it and solve and find cos x. So pretend cos x is the variable, solve the quadratic, and then you've got two equations like this, and they're not too bad. Okay, we can deal with those. Similar sort of things going on here with tan y. It's no good to have tan of 2y and tan y in the same equation, so we need to replace the tan of 2y using our double angle formula. And once we've done that, we can take this, mess around with all the algebra, and turn it into tan y equals root 3 over 7 or tan y equals minus root 3 over 7. Then we can use our graphs to solve that equation. So all the advice that I've given you before is still true. Take what you've got, turn it into an equation with either just sines or just tans or just coses. But now the thing that you're inputting into the sine or the cos or the tan has to be the same. So you can't have a sine of 2a and a sine of a. You can't have a tan of 2y and a tan of y in the same equation if you're going to be able to solve them. So use the double angle formulae and work from there. The reason I skipped over example 10 is because this one is actually a bit fiddly. We've got a cos of theta minus 30 and a sine of theta here. Now you might be led to think, oh well, what I do here is replace this bit with well, if you follow my method, replace this into a capital X and work from there. But actually the trick is that we've got a cos and a sine, so we've got to use our angle addition formula here. Then we can simplify everything down into things to do with coses and sines. And now this is kind of a problem that we're a bit more used to dealing with. We've got coses and sines, and from there we can get a tan. Okay, so get all the coses on one side, get all the sines on the other side, and do a division. Okay, I just think that's a little bit fiddlier than example 11 and 12, so I thought we'd do it afterwards. And then example 13 is really just another one of these showing us that we can do other things. So sine of 2a plus a is the same as sine of 3a. Well, if I think of it as that plus that, I can do an angle addition formula on it, and of course I can give myself a sine of 3a formula, which, as it happens, looks like that. Not something we ever really have to memorise, and when you look at it, hopefully you're quite glad to see we don't have to memorise that, because it stops following anything particularly memorable, doesn't it? And if you imagine if you had a similar one for cos and a similar one for tan, then it would get a bit complicated. But once we've done that, we can work our way through it and spot the link between this expression here and this expression here. They're basically the same thing. I've got 3 and a 4. Well, I've got here a 12 and a 16. They're in the same ratio, aren't they? So if I divide through or factorize these two terms by -3, take a factor of -3 out, then I get an expression of this form, which I can change into sine of 3a and work from there, okay? So instead of having an input of theta here, I want an input of 3 theta, and that's going to make it easier. Now, you might have looked at this one and thought, well, hang on a minute, I thought the idea was get either sine or cos or tan of the same thing. Well, we've got that, we've just got sines, we've just got thetas as the inputs, so this should be solvable straight away. And of course it would be if we had a method for solving cubic equations, because this is a sine cubed. So we don't have a method for solving cubic equations, which is why they've given us a hint of a different method for solving this. If we can solve that equation, that cubic in sine, then we could work from there, okay? Anyway, there's, well, a longer video than I'd planned really, but exercise 7D, there's a few examples of the kind of equations that they now want us to solve.